everyone, this is Joel Smith with the ASQ. It is 1 o'clock Eastern, so we're going to go ahead and get started here. Our two presenters today are Scott Sterbenz and Nicki Brose. Scott's a Six Sigma Master Black Belt at company, but he also in his spare time works with Nicki and the U.S. helps set standards for the equipment of what they do in that role. He also has several 300 games bowling, 6 300 games, and a high 3-game series of 853. So I'm not sure how good of a bowler Nicki is, but Scott's most likely the best bowler we have on the call here. Nicki's with the U.S. Bowling Congress. She's a research engineer, certified Six Sigma Black Belt, and she resides in Arlington, Texas. Like I said before, Nicki works with setting standards for things, and we'll learn today a little bit about how to decide on whether or not to specification for bowling balls.
Muted.
Now, they should have their screen shared so we can see everything. If you do have questions, a chat dialogue webinar interface that will allow you to type in questions and get a response either verbally, maybe at the end of the presentation. So I'll go ahead and thank you, Scott and Nicki.
All right. Well, thanks, Joel, for the wonderful invitation. I hope everyone can hear me okay, and we want to thank the ASQ Statistics Division for inviting us to give this webinar today. So I'm going to switch over to our presentation mode here. Okay, we're going to present today quality sciences in bowling, and specifically answering some decades-old questions with multiple regression and designed experiments. And because this presentation is about bowling, we're going to be giving some little bit of background of the sport and of the United States Bowling Congress first. And then from there, we're actually going to get into the presentation material specifically for which you probably joined in, which is learning a little bit more about central composite design. So first, let's talk about the United States Bowling Congress. The United States Bowling Congress is also known as USBC, and it is the national governing body for the sport of bowling. So this organization provides all of the rules, specifications, and guidelines for all certified league play and tournaments worldwide. And it is dedicated to providing programs and also upholding the game's credibility to preserve its future and enhance the bowling experience. Now within USBC, there's a specific department called the Equipment Specifications and Certification Department. They are the leading source of technical information for bowling, and this is accomplished through expert technical services and sound statistical analyses. So let's talk about what guided the United States Bowling Congress and the Equipment Specs and Certs Department in order to take on some of the projects that we have done over the course of the last 10 to 15 years. So we have known that in many sports other than bowling that there have been significant advances in equipment technology, and these have advanced the ability of participants to score well. Now we also know that there's a lot of advanced coaching within bowling as well, and we believe that that has also enhanced scoring too, as it should. However, the USBC wants to make sure that good scores are achieved through skill and not through technological advances. And we believe that the technological advances in our equipment have artificially inflated scores and therefore jeopardizing the integrity of the sport. If you take a look here at the graph that I show on the screen, you can see that there was pretty much a static level of 300 games, which is a perfect game in the sport of bowling, through about the middle 1970s. And then starting in about the late 1970s, early 1980s, you can start to see a sharp rise in the number of perfect scores in the sport of bowling. And that exponential rise gave us reason for concern. And that's why we've taken on a number of the projects that we have. A number of years ago, there was a study that was conducted by the United States Bowling Congress that looked at the percentage of strikes when the ball hits the pins at a different offset from the head pin center line as you change the angle of entry into the pins. That's what this graph here is showing on the right-hand side of the screen. So you have a low entry angle, which would be considered about 2 degrees. Then you have a 4-degree entry angle, which is shown in red. And then you have a 6-degree entry angle, which is shown in green. So what you see here is that when you take a look at the strike percentage for the 6-degree entry angle versus the other entry angles, you can always see that the strike percentage is higher when the angle of entry is larger into the pins at multiple offsets from the center line of the head pin. Now, scoring in bowling is highly dependent on stringing strikes together. And for many, the most difficult part of the sport is that you can hit the pocket, which is the optimal place to hit the pins, but you may leave a corner pin, which is the 7-pin or the 10-pin in a rack of pins. So if you can increase your entry angle into the pins, you can thereby increase the probability that you're going to carry out those corners or carry the strikes, and as you can get more strikes in a row, your scores are going to be significantly higher. So let's take a look at what has happened with some of the technological advances in bowling balls over the course of the last 100 years or so. Now I'm going to start by talking about cover stock evolution, and then I'm going to move to core evolution. So from about 1900 through about the mid-1960s, rubber was basically the main cover stock that was used on a bowling ball. It does not have a very high coefficient of friction. In the late 1960s, Columbia 300, which is a major bowling ball company, came out with a polyester or plastic shelled ball. This increased the coefficient of friction between the ball and the lane. That was the cover of choice until about the middle 1980s when polyurethane was developed for ball cover stocks. That again increased the coefficient of friction with the lane. And then as we got into the early to mid 1990s, we had reactive resin, which is a specialized form of polyurethane. And then finally in the early 2000s, we had something called particle enhanced resin. So this is the same material as reactive resin, except that they would embed things like mica or carbon or glass chips into the surface of the ball to further enhance the friction. Now let's go about core evolution. So from 1900 through about the mid-1980s, it was a pancake-shaped core inside of the ball. So essentially there was a small weight block in the top of the ball as shown in black, and that was used to replace the weight of the ball that was removed when you would drill the fingers and the thumb holes into the ball. In the mid-1980s, ball manufacturers figured out a way that they could actually now give the core of the ball a shape. And by giving the core of the ball a shape, they were influencing the moment of inertia and the radius of gyration of the ball. By doing that, they were able to start to control the energy in the ball. And then in about the late 1990s, multi-density cores came into play. So the manufacturers of balls figured out how they could use multiple densities inside of the ball for their core in order to further enhance the radius of gyration and also the moment of inertia. So what we see happening is that through the course of time, with greater friction, you are able to increase the entry angle of the ball into the pins. And then, by also using energy management within the ball, you can further enhance that entry angle into the pins as well. Now what I'm going to get into on the next slide are some videos over time. These videos were taken from the Professional Bowlers Tour from the 1970s, 1960s, all the way through modern day. What I want you to take a look at is following this timeline, is that you'll notice from the early balls, you'll see very little entry angle into the pocket. Then with the polyester balls, which will be the next set of videos, you'll see a slightly larger entry angle into the pocket. And then in 1980, you'll also see a greater entry angle into the pocket. Now all of those are controlled by friction. But once we get to the last two sets of videos, you'll see that the entry angle into the pocket was not because the ball was hooking earlier down the lane because of friction. It's because of energy management and friction combined that give the large entry angle into the pocket. So I'm going to break free from the presentation here and open up a video, and we'll take a look at how ball motion has changed through technology over the course of the last 50 or 60 years.
Championship match here at the Firestone Tournament of Champions. We look to the lanes, and in gold and blue, Dick Ritker. Out of the gate. Out of the chute. Now,
heavy for you with a heavy ball.
and John Johnston has opened with a double.
Okay, so you can see very clearly on that set of videos there from the early 1970s, they were using rubber balls. They were playing very close to the center of the lane, hardly any entry angle into the pocket at all. I know those of you watching on the webinar, the video may be a little bit jumpy, and you may not hear all of the audio, but we're trying to do the best that we can for this. So let's watch the next set, which we now move to polyester equipment.
The doubles championship.
Well, they're not splitting the money today.
I don't think so.
15,000 to the winner. Marshall Holman opens the championship match. He does so with a strike in the first frame. A smooth, confident strike. He didn't get a little tired of Marshall taking home the money.
How much of a possible psych job do these two guys do on each other?
Well, they're going to work each other right now.
Well, that's a good way to start.
Mark walking with a superb.
So you could see with that set of videos that players were able to play just a little bit farther out towards the gutter or the channel, and they were able to generate a slightly larger entry angle into the pocket. Now let's move to the late 1980s where we moved to urethane. You're going to see here players playing much farther out on the lane, and that is all again done by use of increased friction.
Weeks average 224. Houston, Texas. "16 titles in a 12-year PBA career. All right, running it out a bit.
So again, all those were done with friction. You can see people moving out farther towards the outside of the lane, and that's how they were able to generate a larger entry angle into the pocket. You'll also notice how the pins look like they're being pushed down. Now that we're going to be moving into reactive resin, you're going to see the balls going a little bit longer down the lane. Okay, so before they start hooking, they're going to be closer to the head pin before they start hooking. But the hook is going to be very sharp, and you're also going to notice a difference in the way that the pins fall now that we have energy management. So here we move to 1995.
And we can see that Handigard is striking on both of them equally well, 11 and 11.
It's an amazing statistic because he's worked really hard on line 30 to get there.
Back in the 70s and lost to Wayne Chester in Salt Lake City, and that has haunted him his whole career.
Well, as we said before, it doesn't get any easier as you go up the ladder. And this is a guy that's led this tournament almost from the get-go.
So what was very interesting with that set of videos there is that you can see that the players were not necessarily playing farther towards the outside of the lane. They were able to play closer towards the inside of the lane, but yet generate the same angle that the same players were able to do several years ago. So in other words, they were using the energy management of the ball to generate the greater angle into the pins. You also should have seen the specific difference in the way that the pins reacted as well. Now let's take a look at 2003, which also shows our point.
You see one guy playing way in, another guy playing pumping it from outside. Each having similar success. A start for Walter Reyes first to this semifinal.
So certainly in that last video you could see how the pins became much more explosive than they certainly had seen back in the days about 30 or 40 years ago. So hopefully that illustrated to you very clearly how bowling ball motion has changed through technology over the years. So now in order for the United States Bowling Congress to do any of our research, we must use what is called a robotic ball launcher. The reason why we use a robotic ball launcher is because the robotic launcher is 100% repeatable and can make shots much more repeatable than any human being can. So I want to give you a short introduction to our robotic launcher that we use at the United States Bowling Congress.
EARL stands for Enhanced Automatic Robotic Launcher. And he's able to throw a ball to within 1/10 of a mile an hour, 1/3 of a board, down the lane, more consistent, more accurate than any human bowler. From a research point of view, it's very important to have an unbiased, very consistent, very accurate representation of the ball going down the lane. EARL can throw anywhere from 0 RPMs to 900 revolutions per minute, 13 miles an hour to 24 miles an hour, right-handed, left-handed, different axis of rotation, different axis of tilt, and basically lay the ball down on any board out on the lane. You can simulate virtually any bowler on the planet.
Okay, so if you caught from the video, some of the main points from the video were a couple of things. One is that the robotic ball launcher is accurate to 1/3 of a board and 1/10 of a mile an hour. He's very, very repeatable. The second thing is that EARL can simulate any bowler on the planet. He can change his speeds, he can change his release, he can change his the rotation of the ball, the speed of the ball, the tilt of the ball as it rolls down the lane. He can essentially simulate anybody. And that gives us a lot of power because it gives us much more flexibility in doing research than using any type of human bowler. So what do we use EARL for? Well, EARL is combined with another technology called Supercats, which stands for a computer-aided tracking system that we use in order to track a ball as it rolls down the lane. So you can see on the picture on the left that we have 23 sensors that are placed down the lane, and they can track critical ball characteristics such as speed, location, rate of revolution, and angle of travel. So anytime EARL releases the ball, these 23 sensors down the lane pick up those critical characteristics and they're fed into a software program. Well, what that software program does is it allows us to plot ball motion down the lane. And when we plot ball motion down the lane, we can see that the travel of the ball down the lane specifically falls into 3 phases. The first phase is a linear phase called the skid phase. The second phase is a parabolic phase called the hook phase. And then the third phase of a ball rolling down the lane is again a linear phase, which we call the roll phase. So we are able to use EARL and the robot previous to EARL along with these sensors from Supercats in order to determine how a ball travels down the lane. Now, as I said before on the last slide, this is just a little bit different view of it. So as the ball travels down the lane, you have skid, which is shown here in light blue. That's linear. Then you have hook, which is parabolic, and that is shown in green. And then the last phase, which is roll, is shown in red. And that, again, is a linear phase. Now, the reason why that's important is because when we bring up the static weight study, which shows the use of our central composite design, you'll see why these 3 phases are important to us. Now I'm going to show you the actual motion of a ball rolling down the lane so that you can see it. I'm going to show you a fast one first, and then I'm going to show it to you in slow motion. So take a look at these. So that was shown in regular so that you could see the phases of skid, hook, and roll, and now I'm going to show it to you in slow motion. Okay, so for those of you that are online with us here with the webinar, I'm sure that you now understand quite a bit more about bowling, maybe more than you care to know about, but you certainly know more about bowling than you did before. Now I'm going to move ahead or back a little bit in time to 2005. In order for us to understand what controls the motion of the ball down the lane, we initiated something called the ball motion study, because we needed to determine which elements of bowling most affected the motion of the ball down the lane. Now understand at this point in time, back in 2005, that there was a lot of disagreement within the industry and within the Bowling Congress itself as to actually what the different properties of the bowling ball have as an effect on the motion of the ball down the lane. And because of this disagreement, it made it very, very difficult for the U.S. Bowling Congress to change and set specifications because of the lack of data that we had to support these moves. So what we did is we set up a typical y equals f of x cascade from our Six Sigma practice, and we used that f of x cascade to determine some predictor variables that we expected to influence ball motion. So those predictor variables included cover stock properties, which included elements of friction and surface roughness. We had core properties, which included RG, differential between RG axes, moment of inertia, so on and so forth. We had drilling properties, which are called static weights. We're going to get into those in more detail a little bit later. So that's how the pro shop or the bowler actually chooses to drill the fingers and thumb into the ball. We have properties of the lane, such as coefficient of friction, the application of oil, which is a conditioner put on the lane. And then we also had environmental properties as well. Now, in order to capture ball motion, we sat down with coaches, players, and other experts in the sport to determine what our response variables were going to be for this ball motion study. And they all related to the way that the ball moved down the lane. Now, to many bowlers, the ones that I've shown here in red are going to be the ones that are going to be most important or most familiar to them. So we call the first transition the point down the lane when the ball transitions from the skid phase to the hook phase. The A score, which will be the sharpness of the hook phase. It will be the sharpness of the break point. In addition, there's the second transition, which is the point when the ball transitions between the hook phase and the roll phase. And then finally, what we call the intended path at 49 and 60 feet, which is, in other words, just a measure of the total number of boards of hook from when the bowler releases the ball on the lane to when the ball finally does hit the pins. So we had 19 response variables and we had 18 predictor variables in this ball motion study. Now what we did with all of this data is that we used multiple regression. And this multiple regression technique was actually explained in an ASQ Fall Technical Conference back in 2007 or 2008. So essentially what we did is we took a look at the p-values for all of the predictor variables for all of the response variables. What we did is when we ran the multiple regression model, the predictor variable that had the lowest p-value would receive a score of 18, and the predictor variable that had the highest p-value, or if that variable was removed because of multicollinearity, that received a score of 1. We did this for each of the 19 response variables. And then at the end, we added up the ranks over all of the 19 response variables for each predictor variable, and we used that sum of rankings in order to determine which predictor variables had the most overall influence on ball motion. Now here's an example of what we did. This is an abbreviated example because obviously I couldn't fit all 19 on the screen here. But you can see for this one here is the intended path at 60 feet, so that's overall hook on the lane. You can see here that when we first ran the multiple regression that we had high variation inflation factor between two of our variables. So we did what we could in order to eliminate the high variance inflation factor to get rid of the multicollinearity, and this is what we were left with. So essentially when we take a look at the p-values, the lowest p-value for this one was the total differential. So that would receive the most number of points. Next, the next highest p-value was the radius of gyration. So that would receive the next highest number of points. Finally, because we removed the ratio of total differential and intermediate differential, which is this ratio here, since we removed that because of multicollinearity, that variable only got 1 point. So we would do that for each of the 19 response variables, sum up these total number of points, and that's how we determine which variable had the most influence over ball motion. And here are the results. This was very, very enlightening for the entire bowling community and was heralded as the capstone study of the United States Bowling Congress thus far. So what we found is that the surface roughness and on-lane and dry-lane coefficient of friction, which are all properties of the cover stock of the ball, had the highest influence on ball motion. Then if we take a look at things like radius of gyration, differential, which is the difference in RG between the high and low axis of the ball, those things are related to the core of the ball. They're second most influential. And then finally, we have things that are called the static weights. So we have side weight, we have top weight, and we have finger and thumb weight that fall way down on the list. Now the ones here that are listed in red, because we always get the question about the ones that are listed in red, these are ones that have an inverse relationship. So the ones that are in blue don't have an inverse relationship, and the ones that are in red have an inverse relationship. So in other words, the higher the RG, okay, the less the ball will move down the lane, whereas the lower the RG, the more the ball will move down the lane. So that's how it has a red bar, because it is an inverse characteristic. So based on what we found in the ball motion study, we set tighter specifications for surface roughness, total differential, and radius of gyration, because they were falling towards the top of our list. However, at the same time, when we were presenting this to the ball manufacturers, we told them that we would investigate widening or removing specifications for static weights, because they fall much farther down here on the Pareto, specifically side weight, top weight, and finger and thumb weight. And this is where we're now going to move into our central composite design, and Nicki Brose is going to be taking us through the rest of the presentation. So I'm going to turn it over to Nicki.
Thanks, Scott. So as Scott was saying, we're looking at these things called static weights, and really, what are the static weights? When you look at the little diagram that we have on the bottom right-hand corner, it shows the finger and the thumb hole where they would be drilled in a bowling ball. Now, based upon the center of grip of that ball, where the grip center line and the grip midline intersect, that's where we measure the weight of the ball off of. We kind of balance it around that point. So side weight is a measure of imbalance between the left and the right side of the ball. Finger and thumb weight is the measure of imbalance between the finger hole side of the ball and the thumb hole side of the ball along that midline. And then we have top and bottom weight. Now the top of the ball is considered to be the side of the ball with the finger and thumb holes drilled in it. The bottom has no holes, so it's exactly opposite of it. USBC currently regulates the static weights on a drilled bowling ball, and we say that there needs to be no more than maximum of 1 ounce of side weight on either side of the ball, 1 ounce of finger or thumb weight, and a maximum of 3 ounces of top weight in a drilled ball. So again, we talked to the ball manufacturers and presented the results of the ball motion study, and we said, well, we wanted to perhaps investigate them a little further because they were a little lower on the list of influence. And there's also been a call from the industry to understand the effect of static weights a little bit further, based on the fact that the limitations on drilling techniques are created because they can only do so much with a bowling ball in order to still maintain the static weight properties within USBC specifications, as well as technology has advanced through time, and we looked at that chart at the very beginning of the timeline, core dynamics have become more and more advanced, so therefore perhaps cover stock and maybe radius of gyration properties and those things, maybe those things are shadowing the effects of static weights, and perhaps the specifications are no longer needed. Do they still matter in today's games? So that's what we were looking at. Blind elimination of the static weight specification was really not in order, because in the ball motion study, we were only able to examine the effects of the static weight specifications, or the effects of static weight within USBC specifications. So what happens if we go beyond those specifications? well, people have run their own little things, they've tried different stuff, and nobody had really ever taken the time to actually measure the effect. So what we did is we developed a 6-factor half-fraction design of experiments with a center point. And we were able to set a high level and a low level for each of our static weight specifications.
That's all right. Sorry about that, Nicki.
That's all right, Scott. We'll wait, give Scott a second to get that back up. Okay, thank you. So we set a high level and a low level to each of the static weight specifications, and these were from a commercially available bowling ball, something that wouldn't be too crazy outside of the box, that could be obtained, but definitely needed to be higher than what our specifications stated. So the corner points maximized the amount of static weight that could be available in a designed bowling ball, and then we also involved factors of rev rate and ball speed and intermediate differential, so the difference between the Y and the Z radius of gyration of the ball. That's, again, the component of saying perhaps maybe core technology and shape would influence or overshadow static weight effects. So it's just something we were curious about. Ball speed and rev rate were included to ensure that if a change were to be made to the static weight specifications, it didn't adversely affect one type of bowler versus another. So we went into and we ran this 32-run DOE, and we were very surprised by the results of the designed experiment. The main effects showed curvature in most of our ball motion responses. So all of those responses that we created for the original ball motion study, we used that as a measurement in this study as well. Several interactions between variables were significant, and that was also very surprising and gave us a really great indication that the design of experiment was really the tool we wanted to be using. Because if we were just to randomly test different levels of static weight static weights in bowling balls, we wouldn't be able to understand the interaction between some of our responses. We did also see an additional observation as we were running through this test. With the high level of static imbalance in a bowling ball, we had a ball that, one of our test balls, that was rolling back down the track that goes underneath the ball return, and it goes down this track, and then it comes up to the ball return back to the bowler who can then use the ball. But the ball then, because there's so much imbalance in it, rolled off the track underneath the lane and actually impacted some of the support structure on the lane. So not only did it damage some of the support structure, but it also took a giant chunk out of our specially made test ball for this particular test. So we were concerned that should this go unlimited, we could see damage to bowling center equipment and our bowlers' equipment as well. And then the most surprising part to us is we discovered a 4th phase of ball motion. Now everything so far that we had seen through the ball motion study or any ball path testing that we were doing had simulated skid, hook, and roll without a problem. But now we're seeing a 4th phase come into play, and sometimes we would see skid, hook, roll, and then the 4th phase would augment into the pins and add extra entry angle. And other times it would actually diminish the angle into the pins, so it would go away from the head pin. This happened regardless of ball speed or rev rate combination. It didn't always happen, but if it did, it definitely did happen at all ball speed and rev rate combinations. And there were several cases where you could, when we plotted all the data points, you could clearly see that there's something else going on after our roll phase, like something else is happening in our graph at the end of the graph. And in other cases, it wasn't as obvious. And in order to find out, we needed to do our due diligence in the analysis process. So again, we had always thought 3 phases of ball motion, skid, hook, and roll, like all of our graphs have come out, everything was looking good. And we developed an algorithm to actually give us these phases and give us the equation for each linear portion as well as the quadratic portion in the center. And what we would do is the skid and the roll phases are linear, and they're calculated first. And we use a linear regression, and once the R-squared value for either one of those phases drops below 99%, that's where we cut off those two linear phases. And all the stuff left in the middle fits a quadratic really, really well. So but what we were seeing in some cases where we were this fourth phase was noticed is that when we analyzed the residuals, and we actually had to ensure that we were doing so, for the roll phase, there were quadratic patterns that were developing. And in that case, if we'd removed those data points from the roll phase, so if you look on this example, if we remove the last 4 data points from the roll phase, the analysis of the residuals worked out just fine. It was very acceptable, and we found a very good fitting quadratic phase at the very end. Now this is really interesting because we end up with skid, hook, and roll, which is very typical, and it's a real pretty ball motion for a bowler's eye. It's very predictable. It gives the bowler what they need in order to make sure that their ball performs predictably and consistently down the lane, and therefore will end up at the pins in the right spot, so hopefully go through the pins and strike. Well, in some cases, we were ending with our skid, hook, roll, and then the ball fades back to the right, so it doesn't go towards the head pin. It actually goes away from the head pin. And in other cases, we would see times where this fourth phase would show up and we'd get skid, hook, roll, and then it kind of hooks again back towards the head pin, then potentially augmenting the angle into the head pin. There's a few things that could be associated with this, and this, from a USB-C standpoint, becomes very undesirable, because if you get a pro shop operator who really knows what they're doing, they could potentially create static imbalance in a bowling ball that would possibly maybe auto-steer a bowling ball down a lane where maybe it could assist a bowler in picking up a 10-pin or even possibly give them an extra little added power into the pocket where they could carry a little better. Again, entry angle from the very beginning of this presentation is very important to bowling. So or if you get somebody who's not as knowledgeable about what they're doing, maybe it could give a bowler an adverse effect on the lane, and therefore they wouldn't be enjoying the game as much, and we don't want to lose members. So it really put us in a bit of a spot where we really didn't want to go out beyond our current specifications. Here's, Scott, are you going to switch to the video?
Yep.
Okay. So we've got a video illustrating the fourth phase of ball motion. Ooh, that one's really quick. But as you can see, at the very end, the ball actually goes back towards the right. So it starts to hook and then fades back towards the right to the 10. Analysis, we knew something was going on. In the very, very center, and that's where our current specifications sit. And we know what's going on in there. We've got skid, hook, and roll. It's happened very predictably in almost all the tests that we've ran. Then once we go to the very outside of this box that you can see, that's where our phase 1 design of experiments was ran at very high levels of static imbalance in the bowling ball. And then we've got all this stuff in the middle, and we're not exactly sure what's going on there. We can't quite predict from the inside box to the outside box because there was some curvature in the model. So we want to know what's going on. Can we possibly expand our static weight specifications further, or is that box all we have? Can they go further? Maybe not to the extremes that we tested at. Excuse me. So what we did is we wanted to set up a second design of experiments that was basically generated from the idea of using a maximum top weight in an undrilled bowling ball, so that through just basic drilling techniques only, there would only be so much imbalance or potential imbalance in the drilled ball. So we used very basic drilling techniques to obtain a measurable axis, and evenly between all three axes, between our finger weight, top weight, and thumb weight would be 3 ounces. And this lent very well to using a response surface central composite design. This is going to allow us to capture the nonlinear effects. It also allowed us to model, and we could evaluate what everybody wanted to know is, what happens if you put a giant amount of static imbalance on one particular axis. And then it also allowed us to understand what happens in the intermediate areas and capture the center point in the middle for us. So the results of this design of experiment was very insightful. We used a very similar ranking system where we weighted the p-values of each input, and then we were able to look at how they ranked amongst each other. And we saw interactions being significant, nonlinear effects kind of floating to the top. But the key factor in here that we can see from this chart is side weight, top weight, and finger weight, 1, 2, and 3, in that order, fell in the exact same order as they did in influence on the original ball motion study. So that was really key for us. The other thing that we found is that a fourth phase of ball motion at these levels of static weights were still present in 2 out of the 15 runs, and they were not in a consistent direction. So in one case we had it augment into the pins, and then in the other case it kind of faded away into the pins. So we're still in this unpredictable area as to an undesirable fourth phase of ball motion is showing up, which we're really not looking for from a performance standpoint. The other component that we're able to look at with the response surface design are these contour plots. And in this example, we held top weight constant, and you can see the effects of side weight and finger thumb weight based on holding on the first transition point. So in the center, you can see that we have a large area where the first transition point is going to be held constant, or not constant, but is not changing as easily. So then it's showing that ball motion is not affected as much as we change some of the static weights within our current specifications. One example that bowlers kind of can really relate to is side weight is the most significant influencer in a lot of stuff, or based on the ranked p-value chart that we saw a couple slides ago. And when we can use the mathematical equation to model and understand what's going on, if we calculated out the attended path at 60 feet, we got a total boards of hook of 4.06 boards of hook, and entry angle in the pins. This is from -3 ounces of side weight to +3 ounces of side weight. We got 0.16 degree. Now, four boards of hook is actually pretty significant to a bowler. But when we think about it a little bit more, that's from -3 to +3 ounces. And typically bowlers are really looking only from 0 to positive when they're looking at their bowling ball. And the other component is that our design of experiments are ran on a very, very flat oil pattern with a low volume and low ball speeds. So if we were to translate that to general bowling conditions or typical bowling conditions, it's our idea that most likely we'll see a little less of an impact on that. And that's a very important thing for us to know, because then we can actually understand that where current USBC specifications are, they're valid and they're important, and the influence of static weights within that range are well understood. So USBC is not going to be making any changes to the static weight specification for bowling balls. Eliminating or expanding those specifications could have led to the unanticipated fourth phase of ball motion, which again could have been problematic for the bowler, the pro shop operator, the manufacturers, and also from an integrity of the sport standpoint, because we really want skill to be the driving factor into a bowler improving and not an artificial method of technology or something to that extent. And we could have very easily seen damage to ball return, lane substructure, and bowling balls. We're not interested in seeing extra damage into bowling proprietors, bowling centers, or our members' bowling equipment. We want them to continue to invest in the sport. And Scott, do you want to wrap up with this last video?
Sure. So this is a very interesting video. There was a professional bowler back in the 1940s. His name was Andy Varapapa, very well known and very well liked player back in the 40s. He had many professional titles, and one of the things that he would often do before with a crowd before and after the television show that you would actually see it on live TV is that he would perform trick shots. And I'm going to show you an example of one of the trick shots that he did that will now look very, very familiar to you.
Oh, Andy wants to show us his way. Oh, well, no picture would be complete without a trick shot from Andy. Oh, brother. Let's see it again, Andy. What the? Now we're doing it with mirrors, is that it?
So hopefully after this presentation you will have seen that that should have looked very familiar to you. He started when he let go of the ball would hook from right to left, and then most of the way down the lane the ball would hook again from left to right, and the audience was always amazed at how he did that, but now from a scientific analysis we know exactly how he did it. For Nicki and I, that concludes our presentation with inviting us to host this webinar today, and we also thank you for your participation in today's presentation.
Well, we thank you, Scott, and Nicki as well for presenting this to everyone. I know this was originally presented at the Fall Technical Conference, so I'm glad we're able to get it out to a broader audience. We did have a couple questions come through the chat. Do you guys want to spend a couple minutes to address those? Or?
Sure.
Yep, that's fine.
One question that came up was whether this fourth phase ever occurred with Earl, and I just confirm, I believe the answer is yes, that all of your experiments were run using Earl, correct?
Yes, that's correct. All of the runs that were in the design of experiments were thrown using Earl. It would be really difficult for us to actually obtain not a significantly visual fourth phase using a regular bowler, just because they're not as repeatable with their hand position as the ball comes off their hand going down the lane. But yeah, all of the throws in both, actually all three studies, the ball motion study, the static weight study phase 1 and phase 2, were all done with Earl.
All right, additionally, it was asked, it looks like only one center point was run in each DOE. Is that correct? And if so, why is there a reason you didn't do multiple center points?
Yeah, actually, I believe it was the first DOE, Nicki, there was one center point that was listed in the matrix, but we actually ran it 8 times.
Correct. Yep.
Okay, excellent. And what were the top 3 recommendations to the U.S. Bowling Congress?
Well, I believe that the top recommendation was that we are certainly not going to adjust the static weight specification from where it currently sits right now. And the reason for that, we kind of summarized that in one of the last slides, was that we had, when you go outside of that specification range, you have an unpredictable and undesirable fourth phase of ball motion, and because you also may have potential damage to the bowling equipment and also to the bowling center, if you have a lot of static weight. Remember, we had that one ball that fell off of the underground ball return track.
Yeah, another recommendation that we've had, actually, and this came more from manufacturer feedback than anything else, is they're interested in us trying to find an area where very similar to the second design of experiments where a maximum top weight could be made into a bowling ball, and then that manufactured ball would be allowable no matter how you drill it. So then that there would only be a maximum potential for once the ball is drilled for static imbalance. So they're interested in us looking into that a little bit further, because where the limits ended up being, we still saw the undesirable fourth phase. So then again, we would have to reduce where we ran the limits at and rerun the experiment to see if we can get to a point either beyond our current specs or where we would be happy with a maximum top weight only specification, understanding the potential for where drilled static weights would end up being.
Excellent. Okay. Now, someone asked about, how the historical weights ended up to be so right. Do you think it was luck, or just people could tell that something would be wrong if they used a different static weight?
Yeah, that's actually a quite an insightful question, and I think Nicki can probably answer that a little bit more accurately than me, but those static weight specifications were set back in when, like the 1940s, was it, Nicki?
That's really my best guess as to when the specifications went into play, because in the 1908 is when, I'm sorry, 1905 is when the maximum bowling ball weight specification was put in at 16 pounds. So somewhere in following that, not too far after that, is when we're saying that most likely static weight specifications started coming into play, because it really wasn't until the 1930s when they started actually using 3 gripping holes in the bowling ball. So we don't actually have a date per se, but it had to have been in there, and it's really our belief that it came from, they watched the ball go down the lane and saw something funny happen, and this was the limit that where things seem to be controlled.
Right.
It doesn't necessarily seem like we have any documentation on experiments being ran, but it seems like that's kind of how a lot of our specifications were originally developed. It was a one factor at a time testing, and okay, here's where things started to look funny, so we put it here.
Okay. And are the static weights affected by the total weight of the ball? And are there certain ranges of ball weights that are allowed to be used?
Yeah, so the answer to both of those questions is yes. So right now, typically the bowling balls range in weight from 8 pounds to 16 pounds, although if you do have a very small or young bowler, some bowling centers do have 6-pound balls and 7-pound balls on hand. So if you've got to figure the total percentage. So if you have a static weight of, let's say, 3 ounces of top weight on a 16-pound ball, it's not going to have as much of an effect as if you have a 3 ounce of top weight on a 6 or 8-pound ball. And actually, a lot of times you can see this when you have very, very young bowlers, so ones that don't have a lot of strength and can't really throw the ball down the lane with a lot of velocity. You will find that the ball does some pretty strange things down the lane because of that.
So the impact is different based on the ball weight.
Mm-hmm.
That is correct. But when you take a look at when you take a look at high school bowling, collegiate level bowling, and amateur and professional bowling, most of the players use weights that range between 14, 15, and 16 pounds.
Okay. Excellent. Well, I think that's the end of our questions. We're going to let everyone know that we do record these, and we do plan on sharing this recording. We have a YouTube channel up now that we will get this uploaded to. We will share that link and paste it on the ASQ Stat Division website so that everyone can link to this as well. If anyone wanted a copy of the PowerPoint, is that available to people? And would you prefer that they contact one of you directly or contact me and I distribute it?
Yeah, what we can do, Joel, is we can send you a PDF of the PowerPoint presentation, and they can contact you, and we'll let you distribute it.
Excellent. So there will be a follow-up email address if anyone is interested in the PowerPoint then. Thank you again, Nicki, and thank you, Scott. Looks like webinar coming up this January. Thanks a
Thank
lot.
you. Yep.